Okay, so when last we were together, we were graphing y equals sine x, and we looked at a couple of the transformations. We're going to continue on with trig graphing, and hopefully my pen seems to be a little more compliant this time. Definitely seems better. Okay, so trig graphing. So recall that we dealt with y equals, and I'm gonna show it to you in the general form. So a sine, or in theory cos, of bx plus c plus d. And so far we've managed to play with a, and we've managed to play with d. And so a, we said, dictated the amplitude, and that was how far away from the center line the function could get. So that was one thing that dictated. It also could do a reflection up and down. So it's called a reflection across the x-axis. And then the d value, essentially the d value, it's a vertical shift. But in the long run, what it really ends up being is it is the center line. So whatever the coordinate is there is going to be the center line for this periodic function. Okay, so what we want to talk about today is, I guess we'll start with just the b value. So those of you who want to play along and do your Desmos, that would be wonderful. And so we're gonna practice a few of these things. But so here's something to try. So how about y equals, it'll be harder to figure out exactly what it is, but we'll get an idea. So y equals, how about the sine of 2x, and we're going to need to put that in brackets, or the sine of 5x. How about the y equals the sine of 0.5x? Okay. Now, it wouldn't be a bad idea for, I'd really like you to actually check those out on Desmos, and come on back, and you're gonna have a pretty good idea. But here we go. So I'm going to sketch, to start with, I'm going to sketch the basic y equals sine x. So here we go. So draw some axes. There we go. And there we go. So if I start with, so in black, I'm going to do, how about we start with just y equals the sine of x. We're going to do that guy in black. Now, we know that it has a period length, and we just have to, this is one of the things you have to memorize. It's got a period length of 360 degrees. In this case, it's got an amplitude of, well, remember, amplitude comes from this a value, and there's no a value showing here, so we really know the a value is 1, so it's got an amplitude of 1. We haven't talked about it yet, but it's got a phase shift that's equal to 0, and it's got a center line. Now, center line is the d value hanging off the back, and there's no value hanging off the back, so in theory, you could say plus 0, and then it makes it obvious that the center line itself has got to be 0. So I'm going to draw this sine function in. I'm going to kind of add a little bit of framing to this just so that it's, makes my life a little bit easier. I'm going to call this right here. Ooh, that's not the right color. Let's get the right color. Come back here. Let's call this one 360 degrees, and I'm going to call this one didn't get it. Call this one 720 degrees. Okay, so there we go. So I'm going to say that one's 720 degrees. So I'm going to label those just so that we know what's going on. So this is 360 degrees, and this is 720 degrees. Now, it's got an amplitude only of 1 for the first one. Well, they all do, actually, in this case. So because of that, I'm going to make this taller just so it's easier to draw. So I'm going to call this one, and I'll call also this one right here. So sine has to finish one complete cycle in that 360 degrees. So halfway is where it's going to cross back over. It's 180 degrees. So we're going to go up. We're going to try and do this as smooth as we can. Not easy to do. Gets right down to 1, and it curves back up. And then it does the same thing again. So it's going to have to hit the halfway point here again. It's not really halfway, close enough. So it goes up to 1, curves around, comes back down smoothly. Okay, so there, this is y equals the sine of x. It is the classic standard, nothing fancy. Well, it's fancy if you've never done it before, but this is the basic y equals sine x. This is something that you're going to have to memorize because this is kind of the parent function, and the parent function tells us, what this thing looks like in general. So make sure that you know that it's got a period length of 360, it's got a center line of 0, and it's got an amplitude of 1. Okay, so there it is. Now, let's go on and we're going to actually sketch y equals the sine of 2x, and we'll use whatever color this is. So I'm going to come along and say, all right, so this one is y equals 2 sine x. Well, if you checked it out on Desmos, you wouldn't have necessarily had exact numbers to see, but what you should have noticed is it's the same height, and it makes sense it's the same height because the amplitude on this guy is also 1, right? If this is a 1 here, then this has got to be a 1 here. It's going to have a center line of 0 because it's not stated, so we could say, a plus little 0 here as well. So it's still got a center line of 0, so it's got the same height. It's centered about the same direction. It's not flipped over because there's not a negative out in front. What this 2 actually controls is the 2 has an impact on the period length. Now, as it turns out, this one is going to have a period length equal to 180 degrees. So that means it has to finish the entire cycle. So it's got to have one full cycle done by the time it gets to this spot right here, because this spot right here, if we gotta go like this, that's not even close. Let's get it closer than that. Oh, dang. So it's gonna be, there's 180 degrees. That's not much better, whatever. There's 180 degrees. All right, draw it in. Okay, that's terrible. So 180 degrees. So it means it's got to have an entire cycle finished by then. So not just, this is only half a cycle, right? A full cycle is from this spot to this spot. It's got to go up all the way down and then back up to the center line again. So here we go. So this one, its halfway point now is here. So that means it's got to get all the way up to 1 and then all the way back down to -1 and all the way back up like that. Put a negative in there. And so that is what this one looks like. It has a much shorter cycle, right? It has a cycle of 180 degrees. So its second cycle, if we wanted to get it in here, it has to finish by there. Up it goes, comes back down, and then it finishes in there. So what happened is it has been shrunk by half. Okay, now I'm going to let you in on a little hint. This letter here, this B letter here, what we can do to figure out our period length is always for sine and cos going to be equal to 360 degrees divided by whatever that B letter is. So if we think about this one, it was going to be 360 degrees divided by 2 is going to be 180 degrees. So that's where that 180 came from. Now this one, similarly, it's going to be 360 degrees divided by 5, which is going to be, I guess that's 72, right? 72 degrees, which is not a very pleasant number. And so it would be hard to fit in here, but you can imagine that is 180, so that's 90. So it would have to finish its entire cycle just in that little spot right there to finish and get it in, okay? And so this one would have a period length of 72 degrees. And then this one, period length is going to be equal to, well, what is the period length going to be equal to? It's going to be equal to 360 divided by a half. So if we come over here and we do, all right, 360 divided by a half is equal to, you can type that in your calculator if you want, it's going to be 720 degrees. So I can kind of fit this one on nicely. I'm going to grab a different color. I think that's red. So we'll say, there it is right there. This guy is going to be that. So it's actually got a period length of 720 degrees, which means that it only finishes one cycle by the time it gets out here to 720 degrees. So that means the halfway point for it is 360. So it's going to go up at a much more gradual pace and then come back down and go through there, Come on down, and up we go, okay? So that is how the b value in this expression impacts the graph. So I'm going to write a little note to that effect, as you should as well. And so we're going to say the b in y equals the sine of bx impacts the period length of the sine, and I'm also going to put in there as well, because it does the same thing, sine and cos graph. To calculate the period length, where did it go? Oh no, what is going on here? There we go. The period length, we can use y, or no, not y. Period length is equal to the unaltered period length, so the regular period length of the function, which is 360, divided by b. Okay, so imagine, as another example here, if we had y equals the sine of 3x, what would the period length be? Well, the period length for this one would be equal to 360 degrees divided by 3, which is 120 degrees. So that means that if it was y equals the sine of x, it would have a period length of 120 degrees. So there we go. The b value in y equals the sine of bx impacts the period length of the sine and cos graph. To calculate the period length, we just do period length, which is normally 360, and we divide it by b, and that's what tells us. Now, what's interesting to note, and it's important for you to realize this, if the b value, okay, so if this b value, if it's greater than 1, so 2 is greater than 1, 5 is greater than 1, it actually shrinks. It makes the period length smaller. And if the period, or if the b value is less than 1 and be bigger than 0, it actually makes the period length larger. 720 degrees is larger than 360. And that's true in general, that the stuff inside the brackets kind of does the opposite of what you would expect. So if you recall, I'm just going to kind of do a quick aside here. Remember when we had y equals a bracket x minus h bracket squared plus k, this was the vertex form of a quadratic. Remember that the h value, this guy in here, was what moved us left and right, and it was always opposite its sign, okay? And that's stuff inside brackets. Normally, when we're talking about transformations, works opposite to what it seems. So a big value doesn't make the function bigger, it makes the function smaller. A small value doesn't make it smaller, it makes it bigger. Stuff inside the brackets works backwards, okay? Lovely. On we go. So now that was the b value. Let's consider the c value, right? So the c value, so if we're just going to go really basic, if we had y equals the sine of x, and I'm going to say plus c. If we want to put minus c, that's okay. In fact, this plus c or minus c works exceedingly similarly to how the vertex form of a quadratic works. This actually is going to impact the shift left and right. So the c value impacts the movement left and right, okay? The d value moves up and down, the c value moves us left and right, and just like the k value does, the movement is the opposite direction okay, so it's the opposite direction to the sine. Okay, and what I mean by that, let's look at some examples. So if we had y equals the sine of, let's say, x minus 30, and I wanted to graph that, okay? This minus 30, okay, what it's going to actually do is it's going to move the function 30 degrees to the right, okay? So because this is negative, but it's inside the brackets does stuff backwards, the minus 30 is actually going to shift it to the right 30 degrees. Similarly, if we had y equals the sine of x plus 50, right? It has to be, make sure it's in brackets, right? If it's not in brackets, it's a d value, but inside the brackets, it's a c value. What that would do is it would move the function, and I'm sure you can predict, it's going to move the function 50 degrees to the left, okay? It's opposite to its sine. I'm going to teach you a little trick in a moment that's going to help us figure out exactly. So this, what this is called, the C value is what impacts, actually it's the whole thing. This whole thing is going to impact the phase shift. Now, phase shift is just a fancy way of saying how much we move left and right. So the movement left and right. Okay, so let's do just a really quick basic example. So how about we actually wanted to graph this one? So let's graph this one right here. Now, we're going to look at all the different aspects here. So I'm going to draw my axes a little bit differently. Okay, I'm going to have more hanging off to the left, and you're going to see why that is. So every time I go to graph one of these things, I always want to list out all the different things. So amplitude, okay, still got my line, there we go. The amplitude, well, what is the amplitude? We know it's the A value, it's not showing, so the amplitude is 1. So we can reach 1 up or 1 down from its center line. Its period length. Period length is equal to 360 degrees divided by the B value. Well, the B value is 1. So, I mean, you could write that if you wanted. You could say, oh, that's 360 divided by 1, which is just 360 degrees. So that's normal, and that's normal. And I'm going to say, oh, the center line comes from the D value. Remember, the D value is always outside of the bracket. So if you wanted to, you could put a little plus 0 in there, and you would realize, oh, the center line is 0. Now, this is where it gets a little more interesting. The phase shift. The phase shift is how much we move left and right. Well, because this is plus 50, it's going to move it 50 to the left. So I'm going to say phase shift is negative 50 degrees. Okay, so how does that help me? Well, we're going to come back here and we're going to say, well, this is 0 degrees, right? Because 0 degrees is on the axis at the origins. 50 degrees would be negative 50 over here. So I'm going to say there's negative 50 degrees. Now, here's where we have to do a little bit more clever math. The period length of this thing is 360 degrees. If we start at negative 50, it's going to travel 360 degrees. That doesn't mean that, oh, I'm going to come out here and I'm going to put a marker at 360 degrees, right? If it started from 0, sure, that's where it would get to. But it doesn't start from 0. It starts from negative 50. So if I start from negative 50 and I travel 360 degrees, I'm going to have to go 50 degrees to get me to 0. And how many degrees are left? Well, there's 310 degrees remaining. So out here is going to be 310 degrees. Now, the way you could do that is you could say, oh, it's negative 50 is where we started, and then I'm going to add 360 degrees. And you can do that on your calculator, and it's going to say, oh, it's 310 degrees. So you start, and I use start in quotes, from negative 50, and we finish, and again, finish is sort of in quotes, at 310 degrees. It's got an amplitude of 1. So the maximum that we can reach up to is 1, and the maximum downwards that we can reach to is negative 1. So I'm going to put in that frame. I've talked about kind of framing things up. Here goes. I'm going to frame this up to help me draw this function. So the highest I can get is there. The lowest I can get to is down here. And I'm going to always kind of put the full frame that I want to get one cycle within. I'm going to put frame. So I'm going to put this frame up here. Now, that's absolutely optional. It just really helps us. Now, the other thing that I want to keep track of here, I hope that's the same color, is I know that it's going to have to cross at the midway point. Now, we know that half of 360 is 180 degrees. So that's the halfway, right? So if I take, and I say, I'm going to start from negative 50, and then I go 180 degrees. So what's negative 50 plus 180? Well, it's 130 degrees. So this is 130 degrees. Clearly, I haven't drawn this to scale very well. Nevertheless, sine starts from the center line and goes upwards normally. So it goes upwards like this. It touches the top, just kisses against it, comes backwards down through here, goes through that spot, comes all the way down to the bottom. It kisses onto that, and then it goes back on up. Now, it's not a V. It's meant to be very smooth. It's just quite challenging to draw this smoothly. Oh, that's terrible. So this is what it looks like. Now, the reason I said in quotes that this is the start is, well, clearly it's not the start. It's going to keep on going. It's going to get, it's going to go over. And similarly, this is not the finish. It keeps on going. But there we go. So this is the C value. What the C value does is it shifts us left and right. Now, there is a complicator to phase shift. Okay, so here is the complicator to phase shift. Imagine that we had not only a C value, but we had a B value as well. Here we go. How about if we had y equals the sine of 2x minus 60? And the minus 60 is in brackets, because if the minus 60 wasn't in brackets, that would be the center line. Because it's in brackets, that is going to help us figure out what the phase shift is. Now, this is where it gets complicated. Let's start going through and listing the things that we need. We need the amplitude. Well, the amplitude in this case, there's no value there, so I know that the amplitude is really 1. Period length. Okay, the period length is going to be impacted, right? Because I know the period length is equal to 360 divided by the B value, which is 2. So the period length is 180 degrees. Another thing that I want the center line. Well, I know the center line is the D value. There's nothing there, so really there's going to be a plus 0 that you could put there if you wanted. I know the center line is 0 degrees. And then we're going to get into phase shift, and this is where it gets complicated. Your instinct, and it would be a good instinct, is that it's going to be plus 60, right? And you think plus because it's the opposite sign, and I love that. That's good. And the 60 because, well, there's the 60 right here. Here's where it gets complicated. This 2 makes a difference to the phase shift. So here's how I'm going to always have you calculate phase shift. So phase shift. Okay, and again, remember that phase shift is how much we're moving left and right. So here's what we're going to do. We're going to take the entire set of brackets, right? So we're going to take this whole thing that's inside the brackets. We're going to take that, okay? So go back here, and we're going to take it, we're going to say 2x minus 60. We're going to take the entire set of brackets, and we're going to set it equal to 0. And then we're going to solve. Now, I'm going to move the 60 over. It was negative. It's going to become positive. So we're going to have 2x equals positive 60. And then I'm going to divide both sides by 2, divide by 2, and we're going to have that x is equal to 30 degrees. This is the exact phase shift, and that will always, always, always work. If you take the entire set of brackets, you set it equal to 0 and solve, the result is your exact phase shift. Now, we knew that it was going to be to the right positive because it's opposite to this sign. What's neat about doing it like this is when you're done your calculation, the result is exactly how much we're going to get moved. So the phase shift here is exactly 30 degrees. And 30 degrees, because it's positive, means we're going to move to the right. And you can put a little arrow there to help you remember that if you want. Okay, so let's look at what the graph of this one would look like. Okay, so here we go. Draw in my axes. Now you'll notice that I've always got a pretty good idea of how to draw my axes. You'll get better at that. So here we go. So we're going to graph this. Actually, I'm going to do this. It's got an amplitude of 1. and the center line is 0. So the center line's here, and then we're going to go up and we're going to say, all right, the maximum we can get up to is 1, and the minimum we can get down to is -1. And then we're going to say, now, here's where it gets complicated. Yes, it's got a period length of 180 degrees. Doesn't mean you're going to hop right out here right away and draw in something at 180 degrees. We're going to take the phase shift into account. We've moved to the right 30 degrees. So I'm going to come out here and say, okay, this is my 30-degree marker. And I'm going to actually draw in my framing right now. So I'm going to put in my upper frame here. I'm going to put my lower frame here. Oh, get back here. Put my lower frame here. Still didn't do it. Fine, whatever. And then I'm going to put a frame there because I know that that's where one of the frames is. Now, look at what we have is we have started at 30 degrees, right? There's 30. And again, in quotes, start. So that's where we start from, in quotes. And then it has a period length of 180 degrees. That means from the start, we're going to travel 180 degrees. So I can say, where am I going to finish? Right? So my finish is going to be, well, we started at 30, and I'm going to add 180 degrees because that's how long the period length is. So my finish is going to be at 210 degrees. So I'm going to come along here, and I'm going to say, all right, well, there's my finish right here. Nope, that didn't work. Let's try that again. My shift is being cantankerous on my tablet here. Still not. Let's try that again. There we go. Okay, so I'm going to, okay. I'm going to say this is 210 degrees. Now, I know that I'm going to need the midpoint in here. Well, two ways we could get the midpoint. We could add these numbers together and divide by 2, and that would get us the midpoint. Or we could say, if one full period length is 180 degrees, that means a half period length is 90 degrees. Okay, so if a half period length is 90 degrees, if we start at 30, we add 90, this is going to give us 120 degrees. So it's sine. Sine starts from the midpoint, and then it goes upwards, and it gets up to the top, and then it curves over. Should get right up and brush against that. Curves over, comes down, gets down to the bottom, curves over, and then goes up and hits here. Now, that is only one period length. Again, it would go on forever. It would keep doing, cycles, and we'd keep doing cycles this direction. But I'm only going to be concerned with you drawing. This was only one period length. We would need to have a second period length out here that we actually finished off. But there we go. So phase shift. I'm going to write those instructions on taking phase shift so that you can have them down as well. So to calculate phase shift, take the brackets that sine or cos is working on, set them equal to 0. That's a terrible 0. To 0, and solve. The result is the exact phase shift. Okay, so let's combine some of this together. Let's do a fully fleshed out, full combination, spicy version of this. So I'm going to graph. I'd like you to try it as well. Y equals 4 sine of 3x minus 90 plus 2. Now, this is a beast, okay? If you've never done them, you're going to get good at these, I promise. But for now, give it a whirl if you want. Otherwise, watch along. So I'm always going to list those 4 things out. Amplitude. Amplitude in this case is 4 because it's the A value. So my amplitude is 4. Center line. Center line is the D value hanging off the back. So my center line is 2. Period length. Period length is pretty easy. We always take 360 and we divide it by the B value. There it is right there. So 360 divided by 3, we're going to find out that it is 120 degrees. So it's got a period length of 120 degrees. Phase shift. Phase shift is the one that causes kids the most grief. What we're going to do is we're going to take that set of brackets, set it equal to 0. So 3x minus 90 equals 0, and then we're going to solve. I'm going to move the 90 over. It's going to become positive. So we're going to have 3x equals 90. I'm going to divide by 3. I'm going to divide by 3. And we're going to get that x is equal to 30 degrees again. So that right there is the phase shift. So let's put all of these pieces together. Here we go. Again, I'm lots of experience doing this, so we're good to go like that. Actually, not quite like that. Let's fix that. Let's put that up a little bit higher. So here's how I'm going to draw these things. I'm going to start by putting on my center line. So my center line is at 2. So I'm going to come up here and say, all right, there's my center line right there. It's at 2. That's my center line. Amplitude is how far away from the center line I can get. So if I start from 2 and I can go 4 up and 4 down. Well, 4 up from 2, if I go up 4 from 2, that's going to take me up to 6. If I go down 4 from 2, that's going to take me down to -2. So I'm going to add those framers to my function. So that's the highest it can get to. This is the lowest it can get to. Now, I didn't do a great job of getting in the center, but let's move the -2 down, or the 2 down to here. And that is the center line. So I'm always going to drop my center line on, reach up however many the amplitude tells me, reach down however many the amplitude tells me, and I'm going to put those in. That forms my horizontal framing. Then I'm going to work on my vertical framing. It's got a phase shift of 30 degrees. Okay, so 30 degrees, and because it's positive, it's 30 degrees to the right. So I'm going to come out here and I'm going to say, all right, this is effectively going to be my 30-degree marker. And I'm going to put in a framer for that as well. There's my 30-degree marker. Now, it's got a period length of 120 degrees. So if I start from 30 and I go 120 degrees. So if I start from 30 and I go 120 degrees, 30 plus 120 says, oh, I'm going to get out here and I'm going to get to 150 degrees. So I'm going to put a framer on that one. And I would need to put one complete cycle, that's what it's called, one period length of sine in there. I want to do 2 of them. So each period length is 120 degrees. So I'm going to go another 120 degrees. If we start from 150, I go 120 degrees. My next cycle is going to finish out here at 270 degrees. And put in another upright like this. And what I can do now is I'm drawing a sine function. Sine starts from its midpoint, it goes up, comes back down, and goes like this. And that's what I'm going to do. I can just follow this pattern really nicely. It's nice to mark in the midpoint so we can see where we've got a cross. So it's got to go up, touch that, come back down, touch this, go back up, touch that, come back down, touch this, go back up, and there we go. Not the smoothest ever because it's hard to draw, but you get the idea that that is what it is. So we have combined, we have dealt with the A value, the B value, the C value, and the D value. Okay, what I'm going to do is I'm going to go up here and I'm going to write a few functions that I would like you to try for some homework questions to practice, and I will post solutions to them tomorrow. So we're going to have, how about you graph y equals 5 sine of, we're going to start with an easy one. How about 6x and then minus 120 degrees plus 1. There's one for you to try. And I'll draw another one up here. How about y equals 2 sine of, we're going to make it a little bit more challenging. How about if we just did 1/2 x and there's not going to be a C value, minus 3. And then one final one. We'll go spicier. How about, and you could check yours on Desmos when you're done. I'm gonna add in a negative. We didn't actually do one with a negative, but you could give it a whirl. So y equals -7 sine of 3x plus, I don't know, 150 plus 1. So there are 3 questions for you to practice. I'll post the solutions to those tomorrow. And tomorrow we will also look at graphing of cosine. Okay, should be good. Thanks.